in MATLAB, working with the new functions. However, there will be a quick PowerPoint presentation to cover the basics. Let's start with a very quick overview of regression analysis. Regression analysis is a type of predictive modeling. We want to model the dependent variable y as a function of one or more independent x variables. We start by specifying an equation that describes the relationship between our variables. This model could be as simple as a straight line, which can be described as y equals mx plus b. Alternatively, we could specify a very complex nonlinear model. The choice of equations is based on our own first principles knowledge about the system that we are modeling. Once we specify this equation, we can use regression analysis to estimate a set of coefficients that minimize the difference between predicted and actual. Typically, we choose a set of coefficients that minimizes the sum of the squared errors. However, in some cases, we might choose an alternative metric. Linear regression is the most commonly used type of regression analysis. Linear regression is used any time that y is a linear function of the regression coefficients. This includes both linear models, such as lines, planes, and hyperplanes, as well as a variety of simple curves, such as polynomials. As we discussed a moment ago, the first step in any regression analysis is specifying an equation that describes the relationship between our variables. In many cases, you won't need to write out the equation. If you are fitting a line or a plane or a hyperplane, MATLAB will do the right thing automatically. However, once you start fitting curves, you need to provide the regression function with more information. You need to explicitly provide a formula that describes the relationship between your variables. For example, let's suppose you're modeling a third-order polynomial, like this cubic equation. You need to pass this information to linear model. Alternatively, suppose that you're working with a second-order polynomial with cross terms. Here, once again, you need to write out this information and give it to linear model. MATLAB has supported regression analysis for decades. MATLAB and Statistics Toolbox have long included functions like polyfit, regress, and regstats. In 12a, we've added a new function for linear regression, linear model. The existing functions will not be removed. All your existing code will continue to work. However, we'd strongly recommend that you consider shifting over to using linear model. Linear model includes a wide variety of helper functions to analyze your data. The MATLAB code that you create is much more compact and readable, almost self-documenting, and we've made some very important discoverability enhancements. Simply put, the new functions are much easier to work with. So enough PowerPoint, let's move into MATLAB and see the new functions in action. Our first example will focus on the most basic type of linear regression, fitting a trend line to two-dimensional data, and fitting planes and hyperplanes to high-dimensional data. These simple examples will let us focus on the syntax for the new algorithms and learn how to access all the built-in functionality. Once we're comfortable with the basics, we're going to move on and consider more complex examples, culminating with some real-world data sets. Let's start by generating some x data, specifying that y is a linear function of x, adding in a noise vector, and then using a scatter plot to visualize the relationship between x and y. We can see what looks like a linear relationship with what appears to be an intercept at around 50. As our next step, we're going to use the new linear model function to model y as a function of x. The output from the linear regression will be saved as an object named myFit, and we can see that myFit is now available in the MATLAB workspace. Now that we've created myFit, we can use the object for analysis. For example, we can use the plot command to plot the resulting model. By default, the plot command automatically displays a scatter plot, just like the one we used a moment before, a trend line showing the relationship between x and y, and confidence intervals for the fit. Note that MATLAB has automatically labeled the axes and added a legend. Now personally, I thought that this plot was a little difficult to read. The markers were a bit small. We can use standard MATLAB plot commands to change the style of the marker. Alternatively, let's assume that you wanted to use the resulting fit for prediction. You might want to use the fit to estimate a plausible y value if x equals 50. This is as easy as applying predict to the myFit object and specifying an x value of 50. Suppose I wanted a bit more information about the resulting fit. I wanted to see the regression coefficients or look at r squared. I simply type display of myFit, and the object is displayed for me. The first line states that this is a linear regression model, while the next uses a formula to display the relationship between x and y. The tilde symbol translates as is modeled as, so this formula states that y is modeled as a function of a constant term and the variable x. Just below this line, we can see the values that were estimated for each of these variables. The estimate for x1 displays the slope of the model. We also have an estimate for the intercept. The display also includes a variety of information to evaluate the quality of the fit. We provide standard goodness of fit measures like r squared, adjusted r squared, and the root mean squared error. You also have access to the standard errors for the coefficients, as well as the t-stat and p-values. All the commands that we just used, plot, predict, and display, are methods. Now, methods are very similar to functions. The big difference is that methods work with objects. From our perspective, the most important thing to understand about methods is that they provide a very easy quality of the fit. We provide standard goodness of fit measures like r squared, adjusted r squared, and the root mean squared error. You also have access to the standard errors for the coefficients, as well as the t-stat and p-values. All the commands that we just used, plot, predict, and display, are methods. Now, methods are very similar to functions. The big difference is that methods work with objects. From our perspective, the most important thing to understand about methods is that they provide a very easy way to discover the new functionality that MathWorks is providing with Linear Model. Watch what happens when we type methods of myFit. We immediately get a list describing all the different methods that are available for this object. For example, we can see plot, predict, and display listed. And there are also a whole bunch of other methods that you might never have known about before now. For example, we have a method called plot residuals. Let's see what we can do with it. If I enter plot residuals of myFit, I generate a plot that displays the fitted values on the x-axis and the size of the residuals on the y-axis. This type of plot is very useful to see whether the size of the residuals is constant across the dataset. If not, this suggests that the dataset exhibits heteroskedasticity, which can present problems for certain types of analysis. And just looking at the help shows me that I can also generate a probability plot and check whether or not the residuals are normally distributed. Let's quickly look at another method, plot diagnostics. I know that outlier detection is of interest to a lot of Statistics Toolbox users. We can use a metric known as Cook's distance to look for potential outliers. Cook's distance measures how the results of a regression would change if a given data point were deleted from our data set. Any data point whose Cook's distance is significantly greater than 3 times the mean might merit special consideration. For example, in this chart, we might want to look at observation number 44 and see if there's something unusual about that data point. As I mentioned a moment ago, looking through the complete set of methods is a great way to discover different analysis routines and plots that are available to you. I'd also like to point out another great discoverability improvement in the 12A release. You can use the MATLAB variable editor to walk through this object. As you can see, there's an object named MyFit available in the MATLAB workspace. If I double click on this object, it gets blown up and displayed inside of the variable editor. And there's all sorts of information available to you. Let's assume that you wanted the formula for an object. Simply double click on the formula field and you can access the formula either as a MATLAB anonymous function or alternatively displayed using what's known as Wilkinson's notation. Alternatively, let's assume that you wanted the fitted values that correspond to each x value. Perhaps you'd like to plot the y values versus fitted values and see whether or not they fall on a 45-degree line. All the information you need for that is contained inside of the field called fitted. Last but not least, suppose you wanted to look at the actual numeric values for Cook's distance. All of that information is available inside of a field called diagnostics. So far, all of the examples we've been working with have been simple trend lines. We're modeling dependent variable y as a function of a single independent variable x. Let's branch out a bit and consider a surface fitting problem. Here we're going to generate a plane that is the best fit for independent variables x1 and x2. Now, notice that the syntax for performing this fit is identical to that used in our first example. However, if we look at the output, we see that the resulting model contains 2 independent variables. In a similar vein, with 4 independent variables, the linear model will default to fitting a hyperplane. Note that I just used the word default. Back during the PowerPoint presentation, I noted that regression techniques require you to specify a model that describes the relationship between your variables. So far, we haven't needed to do so. And the reason is that all of our data was generated in such a way that it conforms to our default models. Straight lines for 1 independent variable, planes for 2 independent variables, hyperplanes for high-dimensional data set. Let's turn to some more interesting examples where our data should be modeled using something other than a straight line or a plane or a hyperplane. Census is a data set that ships with MATLAB, which shows the population of the United States over time. As you can see, the relationship between population and time clearly doesn't appear to be linear. However, it does look as if a quadratic might do a good job modeling this data set. Here, once again, we'll use linear model to model our dependent variable population as a function of the independent variable time. We don't want to fit a straight line to the data set, which means that we need to instruct linear model regarding what type of equation should be used to describe this relationship. This is as simple as passing in the string quadratic. Note that when we display myFit, the formula now includes a constant, a first-order term, x, and a second-order term, x squared. And linear model has estimated coefficients for each of these. Just like before, we have access to all of our methods. For example, we can generate a plot of the resulting fit using the plot method. Here's where life starts to get interesting. Rather than passing in the string quadratic, there's actually a variety of different input strings that we could have used to generate the same model. Look what happens when we input poly2 instead. We've described the same model and generated the exact same set of regression coefficients. In a similar vein, I could have described the quadratic using the same formula notation that MATLAB uses to display the model. And once again, this will generate the same model and the same set of regression coefficients. Right now, you're probably asking yourself, why are there so many different ways to describe a quadratic? To understand what's going on, we need to look at a much nastier model. Let's consider a data set that needs to be modeled using a high-order polynomial with a bunch of cross terms. Something like the following mess, which contains cubics and quadratics and the like. To start with, this example does a great job explaining why we can't rely on simple strings like quadratic or cubic. This type of shorthand works great for simple low-order models. However, once the models get complicated, it really isn't practical. Next, consider what happens when I run linearmodel.fit using poly33 as the input string. As you can see, linear model was able to build a very complicated model based on a very simple expression. Formally, the poly33 syntax means build a model with all terms up to and including x1 cubed and x2 cubed. Cross terms are allowed so long as the terms don't sum to more than 3. So x1 squared multiplied by x2 is legal, since 2 plus 1 is equal to 3. However, x1 squared multiplied by x2 squared is illegal, since 2 plus 2 is greater than 3. The poly33 syntax is a brute force instrument. It builds a complex model with a lot of cross terms. However, you don't have fine-grained controls over what terms will be included. If you prefer, you also have the option to type out the entire model. And this option does give you that fine-grained control. However, it also requires a lot of typing. Now, the language that we use to describe these models is called Wilkinson's notation. Wilkinson's notation is actually quite powerful. Once you understand it, you'll be able to learn some very nice shorthand. For example, look at the following formula. The x1 cubed times x2 cubed statement instructs a linear model to include all terms and cross terms up to and including x1 cubed multiplied by x2 cubed. However, we're also subtracting all terms and cross terms up to and including x1 squared multiplied by x2 squared. What's left? Only those terms and cross terms that explicitly include x1 cubed or x2 cubed are included inside the model. Wilkinson's notation might seem a little bit strange at first. However, any statisticians who are watching have probably seen this before. The notation does take a bit of work to get used to. However, if you need to build complicated custom linear models, this is really the best way to go. If you want to learn more about the notation, you can search on Wilkinson inside the Statistics Toolbox help, and you'll get a nice write-up about the notation, as well as a link to Wilkinson's original paper. At this point in the presentation, I inevitably get asked, where are these models coming from? How do you know what terms to include inside of the model? For that matter, how do you even know what variables should be used? Now, if you're lucky, you know all this information a priori. Your own knowledge about the dependent variables, which include the tax rate, the average age of the houses, the student-teacher ratio in local schools, geographic information, information about air quality, and the like. Our goal is to build an accurate predictive model and simultaneously identify which variables have the greatest amount of predictive power. Our data is stored in an Excel file named housing. As a first step, we're going to import the data into MATLAB and store it in a dataset array. In case you haven't seen them, our data is stored in an Excel file named housing. As a first step, we're going to import the data into MATLAB and store it in a dataset array. In case you haven't seen them before, dataset arrays are data containers that are included with Statistics Toolbox. And dataset arrays have a lot of nice properties for storing tables of information. Dataset arrays have named columns, and the column names were automatically generated based on the column headers in the Excel spreadsheet. Dataset arrays are also able to store heterogeneous data inside a single container. If you look closely, you'll see that most of the columns contain numeric data. However, one of them, Charles River, consists of cell strings. The last column, column number 17, is our dependent variable, the median home price. Now please note, we're using a famous data set that dates back to the mid-1970s, and this explains why the housing prices are so low. As a next step, let's convert Charles River from a cell string over to a nominal array. And using a nominal rather than a cell string is good practice because it will save us memory. And if this were a larger data set, that could actually be very significant. Next, let's generate a regression model using linear model. Linear model is smart enough to recognize that our data is stored in a dataset array, and this will impact the regression in a number of ways. First of all, notice that I don't need to specify x and y variables. I'm passing a single variable, housing, to linear model. By default, linear model assumes that the last variable in the dataset array is the dependent variable and that all the other variables are independent variables. You can override this if you want, but it's a good way to save some typing. Also note that the column names from the dataset array have automatically been used as variable names inside the resulting fit. And finally, note that we have a variable called Charles River Yes. As you might recall, Charles River is storing categorical data. This says whether or not the census tract abuts against the Charles River. When you work with categorical data in a regression, you typically need to create dummy variables. Linear model automates all of this for you and automatically generates an appropriate set of dummy variables. As you can see, our regression model includes 16 independent variables and has an R-squared of about 0.75. Let's see if we can improve upon this using a technique known as stepwise regression. Rather than using linearmodel.fit, I'm going to enter linearmodel.stepwise and kick off stepwise regression. Stepwise regression is a feature selection tool which is used to determine which set of variables has a statistically significant effect on the performance of the model, in this case on the accuracy of the model. Stepwise regression adds variables to the model one at a time. It determines which variable improves the model the most, and then tests whether the new model is significantly more accurate than the old model. If the new model is significantly better, we find the next best variable to add. If the new model is pretty much the same as the old, we remove the last variable and we stop. In this example, we're testing every independent variable to see whether it has a statistically significant effect on the model. As you can see, the most significant variable was lower status, which measures the percentage of the population that was considered to be lower status. And the next most significant variable was the average number of rooms in the building. Once variables have been determined to be statistically significant, cross terms for those variables also get added into the mix. For example, the term lower status times number of rooms shows up immediately after these two variables were identified as being significant. Okay, our regression model has now finished running. And as you can see, the resulting model is much more complicated. Our model includes 12 predictors, but 35 different terms. However, the model also has much more predictive power. Our model is now explaining about 90% of the variance in the data set, rather than the 75% in our original fit. As always, you have the option to customize your analysis. For example, this next line of code modifies the behavior of stepwise in two important ways. First, we are restricting stepwise to only consider simple linear models. Cross terms are excluded from the set of variables, and this means it will eventually end up with a simpler model. Second, by default, stepwise measures the accuracy of the various models using the sum of the squared errors. Here we're changing the criteria to use AIC instead. The resulting model has an R squared of 74%, so we're explaining roughly 74% of the variance in the underlying data set. This is an interesting result in that we're able to achieve essentially the same level of accuracy as our original linear model. However, this time around, we've decreased the number of explanatory variables from 16 down to about 11. So, what's the big takeaway from this example? Stepwise regression provides a powerful tool for model evaluation. We started with 16 different explanatory variables that we knew very little about. We're able to use a simple one-line command to identify which of these variables has a statistically significant impact on the model. We're also able to use simple parameters to control the complexity of the resulting model by limiting the use of cross terms. So far, we've restricted our discussion to linear regression. However, Statistics Toolbox also includes new functions for